My name is Peter and I work for Cake Solutions. We are a consultancy company focusing on building reactive and data processing applications using technologies such as Scala, Apache, Spark, and many others. In this presentation, I'm going to talk about distributed stream processing. This area attracts quite a lot of attention these days, and I firmly believe you will find next 45 minutes interesting. So what am I going to talk about? I will start with a short introduction. What are the reasons behind this increasing demand for real-time data processing and how to address it? Then I'm going to talk about stream processing in general and also about the challenges we have to expect. After that, I'd like to talk about available frameworks. What are the similarities and differences, and also their typical use cases. Finally, we will conclude with general guidelines and recommendations. I like to say this talk is based on my personal opinions, and I'm definitely biased in some way. Huge amounts of data has to be processed fast from a rapidly growing set of disparate data sources, like trading, social networks, IoT, system monitoring, and so on. And this pushes limits of the traditional batch processing infrastructures because they are often simply not good enough. And stream processing might be a good way to go. We want to process incoming data on the fly, and we want to be able to react to events as they occur, as the latency really matters here. And as you suspect, distributed stream processing is continuous processing, aggregations, and analysis of unbounded data. It is a general computational model as MapReduce, but we expect our latencies in millis or in seconds. These systems are usually modeled as directed acyclic graphs, DAGs, or DAGs. DAG is a graphical representation of chain of task, and we use it for description of the topology. I will help myself with your terminology from Apache streams a little bit, but I'm sure it will be clear anyway. So as you can see in the picture, data flows through chain of processors from sources to sinks, and which represents the streaming task. And speaking about Apache streams, I think it's very important to emphasize the word distributed, because even local solutions can create and like DAG, but we are going to focus only on solutions running on multiple machines. When choosing between different systems, there is a couple of points we should take care of. So let's start with the runtime and programming model. The programming model provided by platforms determines all of its features and should be sufficient to handle all possible use cases for an application. This is a very crucial topic, and I will come back to it very soon. The functional primitives exposed by a framework should be able to provide rich functionalities at individual message levels like map or filter, which are pretty easy to implement even if you want to scale a lot. But it should also provide across message functionalities like aggregations and across streams operations like joins, for example, which are much harder to scale. And state management. Most of applications have some kind of stateful processing logic that requires maintaining a state. And the platform should allow us to maintain access and update the state information. For message delivery guarantees, we have a couple of classes like at most ones, at least ones, and exactly ones. Another important thing to consider. Failures can and will happen at various levels like network partitions, disk failures, or nodes going down, and so on. And we expect our platform should be able to recover from all such failures from their last successful state before harming its result. And then we have more performance-related requirements like latency, throughput, and scalability, which are obviously extremely important in streaming applications. We should also take care of maturity and adoption level. This information could give us a clue about potential support, available libraries, or even Stack Overflow answers, and so on. And also, last but not least, the ease of development and the ease of operability. You know, it's great when we have like a super fancy system which covers all of our use cases, but if we cannot write a program for it, or if we cannot deploy it, we are done anyway. So let's talk about runtime and programming model, which is probably the most important trait of the system, because it defines expressiveness, possible operation, and future limitations. Therefore, it defines system capabilities and its use cases. There are two distinctive approaches how to implement streaming system. First one, the native streaming. It means all incoming records, or events if you will, are processed as they arrive, one by one. Second approach is called micro-batching. Short batches are created from incoming records and go through the system. These batches are created according to predefined time constant, typically every couple of seconds. Both approaches have inherent advantages and disadvantages. So let's start with native streaming. The great advantage of native streaming is its expressiveness. Because it takes the stream as it is, it's not limited by any initial abstraction over it. Also, as the records are processed immediately upon arrival, achievable latencies of these systems are always better than its micro-batching companions. Apart from that, stateful operations are much easier to implement, as you will see in the next couple of minutes. A native streaming system have usually lower throughput, and fault tolerance is much more expensive, as system has to take care of every single record. Also, load balancing is kind of issue. Let's say we have a data partitioned by a key, and we want to process it. If the processing of some key of the partition is more resource intensive for any reason, this partition quickly becomes jobs bottleneck. Splitting stream into micro batches inevitably reduces system's expressiveness. Some operations, especially state management or joins and splits, are much harder to implement as system has to manipulate with whole batch. Moreover, the batch interval connects two things which should never be connected: an infrastructure property and a business logic. On the contrary, fault tolerance is much simpler. A system just sends every batch to a worker node, and if something goes wrong, it can just use a different. Lastly, it's good to remark, we can build micro-batching system atop native streaming quite easily. Programming models can be classified as compositional and declarative. Compositional approach provides basic building blocks, like sources or operators, and they must be tied together in order to create expected topology. New components can be usually defined by implementing some kind of interfaces. On the contrary, operators in declarative APIs are defined as higher-order functions. It allows us to write functional code with abstract types and all its fancy stuff we love, and system creates and optimizes topology itself. Also, declarative APIs usually provide more advanced operations like windowing or state management out of the box. I'm going to show you some code samples very soon. There is a number of diverse frameworks available, and it's literally impossible to cover all of them in just one session. So I have been forced to limit it somehow, and I decided to go for a popular streaming solution from Apache landscape. Therefore, we are going to focus on Apache Storm and its sibling Trident, and on streaming module of very popular Spark. We are also going to talk about streaming system behind LinkedIn named Samza. And finally, we are going to discuss two promising Apache projects, Apex and Flink. I believe this is a great selection because even if all of them are streaming systems, they do approach various challenges very differently. Unfortunately, I won't talk about proprietary streaming system like Google Mealwheel or Amazon Kinesis, and also we are going to miss interesting but still limited adopted systems like my beloved Intel GPump. So that may be for next time. Apache Storm was originally created by Nathan Martz and his team at Backtype in 2010. Later it was acquired in open source by Twitter, and it became Apache top-level project in 2014. Without any dubs, Storm was pioneered in large-scale stream processing and became de facto industrial standard. Storm is a native streaming system and provides low-level API. Also, Storm uses Thrift for topology definition, and it also implements Storm multi-language protocol. This basically allows us to implement our solutions in a large number of languages. And of course, Scala is one of them. Trident is a high-level micro-batching system built atop Storm. It simplifies topology building process and also adds high-level operations like windowing, aggregations, or state management, which are not natively supported in Storm. In addition to Storm, Trident provides exactly once delivery. Trident has Java, Clojure, and Scala APIs. As we all know, Spark is very popular batch processing framework these days, with a couple of building libraries like Spark SQL, mmlib, and of course, Spark Streaming. Spark's runtime is built for batch processing, and therefore, Spark Streaming, as it was added a little bit later, does micro-batching. The stream of input data is ingested by receivers, which create micro-batches, and these micro-batches are processed in a similar way as other Spark jobs. Spark Streaming provides high-level API in Scala, Java, and Python. Samza was originally developed in LinkedIn as a proprietary streaming solution, and with Kafka, which is a great LinkedIn contribution to our community, it became a key part of the infrastructure. As we are going to see a little bit later, Samza builds heavily on Kafka's log-based philosophy, and both together integrates really well. And also Samza provides compositional API. Apex is a Hadoop-focused streaming system backed by Exahu engineers. Right now, it provides compositional API for Scala and Java. You can also use its visual tool for assembly application, which is kind of a nice feature. Also, high-level API is under construction. Apex also comes with a library of operators named Malhar. And as I'm going to show you a little bit later, Apex implements interesting compromise between native streaming and micro-batching. And the last but not least, Flink. Flink is a pretty old project. It has its origin in 2008, but right now it's getting quite a lot of attention. Flink is a native streaming system and provides a high-level API. Flink also provides API for batch processing like Spark. But there is a fundamental distinction between these two. Flink handles batch as a special case of streaming. Everything is a stream, and this is definitely better abstraction because this is how the world really looks like. So that was a quick introduction of the systems, and as you can see on the table, they do have pretty different traits. Now let's take a look at code samples, and of course, nothing is more important than counting words. You know, word count is something like hello world of data processing. So let's start with Storm. And please note, the example was simplified significantly. First, let's take a look at its topology definition. As you can see, we have to define a spot, or if you want, a source. And there is a both, a processing component, which splits text into the words. Then I have defined another board for actual word count calculation. Also, take a look at the magic numbers, 5, 8, and 12. These are the parallelism hints, and they define how many independent threads around a cluster will be used for execution of every single component. As you can see, all is very manual and low level. And let's focus now how is the actual word count board implemented. As long as Storm does not have inbuilt support for managed state, so I have defined local state, which is far from being ideal, but let's say it's good as a sample. Apart from that, it's not very interesting, so let's move on and take a look at Trident. As I mentioned before, Trident is Storm's micro-batching extension, and Trident, apart from many other goodies, provides data management, which is pretty useful when implementing word count. As you can see, I could use high-level operations like each and group by, so it is a little bit better. And also, I was able to use Trident manage state for storing counts. And now it's the time for a pretty declarative API provided by Apache Spark. Also keep in mind, on the contrary to previous examples, which were really simplified, this is nearly all code you need to run this simple streaming word count. Every Spark streaming job requires streaming context, which is basically an entry point to the streaming functionality. Streaming context takes a configuration, which is, as you can see in our case, very limited. But more importantly, it defines its batch interval, which is set to 1 second. And now you can see whole word count computation. Quite different, isn't it? That's the reason why Spark is sometimes called distributed Scala. As you can see, it's quite standard functional code, and Spark takes care of the topology definition and its distributed execution. And now the last part of every Spark streaming job, starting the computation. Keep in mind, once started job cannot be modified. Now let's take a look at Apache Samza, another representative of compositional API. The topology is defined in Samza's properties file, so we will find it here, but for us it's important. The task has defined its input and output channels, and communication goes through Kafka's topics. In our case, whole topology is this word count task, which does all the work. In Samza, components are defined by implementing particular interfaces. In this case, it's a stream task, and I have just overridden the method process. Its parameter lists contain all what's needed for connecting with the rest of the system. And the computation itself is just a simple Scala. And now it's time to take a look at Apex. As you can see, it's a classic compositional API, and again, the snippet was simplified. Firstly, you have to define jobs topology. We have to add components to DAG and connect them with streams. And here's the definition of one of the operators. This one splits incoming strings. The code itself is pretty clear, I guess. Now let's take a look at Flink. As you can see, API is pretty similar to Spark streaming, but notice we are not setting any batch interval. Computation itself is pretty straightforward. There's just a couple of functional calls, and Flink takes care of rest. And now it's time to look at more interesting problems of streaming processing, starting with fault tolerance. You know, fault tolerance in streaming systems is inherently harder than in batch. When facing an error in batch processing system, we can just restart that part of the computation, and we are good. But this is much harder in streaming scenarios because data are still incoming, and a lot of jobs can run 24/7. Another challenge we have to face is state consistency, because in the end of the day, we have to start replaying events. And of course, not all state operations are idempotent. As you will see, fault tolerance can be pretty hard. So let's take a look how our systems deal with that. Storm uses a mechanism of upstream backup and record acknowledgements to guarantee that messages are reprocessed after a failure. Acknowledgement works as follows. An operator sends back to the previous operator an acknowledgement for every single record that has been processed. And the source of the topology keeps a backup of all records it generates. One receives acknowledgements from all generated records until the syncs. The backup can be discarded safely. At failure, if not all acknowledgements have been received, then the records are replayed by the source. This guarantees no data loss, but just result in duplicate records passing through the system. It's basically at least once delivery for us. Storm implements this with a clever mechanism that only requires few bytes storage per source record to track the acknowledgements. But in general, people record acknowledgement architectures, regardless of their performance, fail in offering exactly once delivery. thus burdening application developer with reduplication. Also, Storm's mechanism is low throughput and has problems with fault control, as the acknowledgement mechanism often falsely classifies failures under back pressure. Spark streaming and its micro-batching semantics follow a different approach. The idea is terribly simple. Spark processes micro-batch on various worker nodes, and each micro-batch may either succeed or fail. At a failure, the micro-batch can be simply recomputed, as they are all persistent and immutable. So exactly once delivery made easy. Samza's approach is also very different. It takes an advantage of durable offset-based messaging system. It's usually Kafka, of course. Samza monitors offsets of this task and moves it when message is processed. Offset can be checkpointed in a persistent storage and restored in case of failure. The problem is when it restores offsets from the last checkpoint, it does not know which upcoming messages were processed, and it might do it twice. So that's at least once delivery for us. As we know, there are two distinctive approaches how to implement stream processing: the native streaming and the micro-batch. Apex takes a little bit different, I would say a hybrid approach, which they called Windows Stream Real-Time Event Stream Processing. So what does it mean? Basically, Apex periodically sends some kind of markers named beacons for a stream, and they are used to track the process events in case of failure. It works quite well. It's efficient. There's no artificial latency. But as you may see in the picture, your application windows must be multiples of the system windows, and that might be a limiting factor. Flink approach is based on distributed snapshot, which keeps the state of streaming job. And it is kind of similar to Apex. Flink's markers are called barriers and are sent through the stream. When barrier reaches the operator checkpoints corresponding part of the stream. So if we compare it to Storm, it is much more efficient, as it does not have to acknowledge every single record, but does it in small batches. But don't be confused, this is still native streaming. Conceptually, it is very different from Spark. And also Flink's windowing is not limited in any way. Lastly, both Apex and Flink provides all delivery guarantees. Most of the non-trivial streaming applications have some kind of state. On the contrary of stateless operations, when we have just an input, then processing and an output, we have an input and a state, then we do processing and we have an output with a modified state. We have to manage our state, persist it, and in case of failure, we expect our state to be recreated. The recreation of the state might be a problem a little bit, as we do not have always exactly one's guarantee. So some of the records may be replied multiple times, and this is not what we want usually. As we know, Storm provides at least once delivery guarantees. So how can we achieve exactly one semantics provided by Trident? Conceptually, it is quite simple. You just start committing your records, but obviously it is not very efficient. So you start doing in small batches, then do some optimizations, and here we are. Trident provides a couple of dedicated components for storing states, which can be accessed by streams. It's not very convenient, but it's definitely usable. When thinking about stateful operations in stream processing, we usually have a long-running operator with a state and a stream of records passing through it. And as we know, Spark streaming is micro-batching systems, and therefore is implemented differently. Basically, Spark streaming manages state as another micro-batch stream. So during processing of each micro-batch, Spark takes a current state and a function representing the operation, and the result is a process micro-batch and an updated state. Some of the solutions for everything is just push it out to Kafka and problem solved. And it also works in the context of state management. Samza has real stateful operators, so any task can hold a state, and the state changelog is pushed to Kafka. If needed, state can be easily created from Kafka's topic. To make it a little bit faster, Samza allows us to plug in key value stores. as local storage, so it doesn't have to go to Kafka all the time. Unfortunately, Samza provides at least once delivery only, and it hurts a lot, but the implementation of exactly once delivery is planned. Apache Apex maintains two types of states. Firstly, Apex gives us a fancy ability to change its topology dynamically on runtime. So it resist and persists its DAG into a persistent storage, usually HDFS. Apart from that, Apex provides both stateless and stateful operators. As you can see in the picture, Apex provides long-running operators, conceptually very similar to Samza, and their state is, of course, saved into persistent storage. Flink provides stateful operators like Samza or Apex. When working in Flink, we can use two different types of states. First one is a traditional or local state, if you will. It is a current state of particle operator instance only. These guys do not interact between each other. Apart from that, Flink provides partitioned or key state, if you will, which basically maintains state of whole partition. So let's take one more look how to count words, focusing on state management. So let's start with Trident. You may have seen a snippet already, as it is fairly similar as before. We can create a state by calling persistent aggregate. Important argument is count, which is a building component for storing numbers. As I said, if you would like to process data from it, you will have to create a stream for that. Sparse declarative approach is a little bit better. First, we have to create RDD used as an initial state. Then we have to define a transition function which takes a word, its count, and a current state. This function does the computation, updates the state, and returns a new result. Finally, we can put all bits together and get a state stream which contains our word counts. So let's take a look at Samza. Firstly, we need to define our state. In this case, it's key value store, and we also have to define how it should be initialized. And then we can use it during computation. As you can see, it is pretty straightforward. Apex's snippet looks also similar as before. I have just added counter, a building component for counting words received on its input port. But I could also add a state to any other component if needed. Simple. And finally, let's take a look at Flink. Flink provides a very nice and neat API. We just call a function map with state, which takes as an argument function with two parameters. First one is a word to process, and the second one is a state. Function returns processed output and a new state. I really wanted to show you some nice performance comparisons, but I will not. A reasonable comparison is a topic probably for a whole talk, maybe more, and I won't do it here, but a couple of guys did it already, and I'm really happy to reference them. So for now, just in general. When we talk about performance in stream processing, we mostly talk about latency and throughput. It depends on many variables, but in general and for a really simple task, we can expect hundreds of thousands or even millions of records being processed per node per second. Good thing is that these systems have considerable horizontal scaling capabilities, so we can usually adjust performance according to our needs or according to our budget. For latency, in case of micro batch, we're usually thinking in seconds. In case of native streaming, we can expect lower hundreds of millis for most of the systems, but Tune, Storm, or Apex can operate in tens or under really good circumstances, even in milliseconds. Also, it's important to keep in mind the cost of derivative guarantees, fault tolerance, and state management. For example, turning on fault tolerance may cost you like 10 to 15%, but in case of Storm, it could be like 70% of your throughput. So there is no free lunch, as always. And during the talk, I have shown you stateless and stateful word count examples, and of course, stateless will be faster. In case you're wondering how much, So in the context of Apache Flink, the difference was like 25%, but in case of Spark, it was around 50%. I'm pretty sure it can be tuned, but this could give us an idea. This is something what we should have in mind. And speaking about tuning, all systems have very rich tuning options which may lead to significant performance gains, and you should always try and find time to take a look at it. Also, it's important to have in mind all operations are distributed, and sending data through network is a very expensive operation. So try to take an advantage of data locality, and also try to tune up your application's realization. I just love to discuss about the performance. Hope I gave you basic ideas what to expect, but we have to move on. When picking up the framework for your application, you should always consider its maturity. So let's take a quick look. How does it look like in our cases? Storm was the first mainstream stream processing system and is used by many companies. As an example, we can have Yahoo and Spotify, but there are like tens of them, maybe hundreds of them. Spark is one of the most trending Scala repositories these days, and one of the engines behind Scala's popularity. Spark's adoption grows every day. It's used by companies like Netflix, Cisco, DataStax, IBM, Cake Solutions, and so on. Samza is used by LinkedIn and also by tens of other companies. As an example, we can have Netflix or Uber. Although Apex graduated very recently, it has been adopted by a couple of corporate clients like GE Predix Cloud, Capital One, or Silver Spring Networks. And I'm pretty sure more are on the way. Flink is also an emerging project, but we can see its first production deployments, and again, I'm sure more will follow very soon. For example, I heard Amazon was awaiting it, and also Capital One is using it, and so on. So we have just finished basic comparison of chosen systems, which took me most of my time. And we discussed how do they approach various challenges which needs to be sorted out when implementing distributed stream processing system. You may take a quick look at a summary of, from my opinion, their key traits. And now is the time to move on the last part of this talk, framework recommendations. I have to say, this part is the most opinion-based by far, but I was really trying to be fair. So let's move on. The answer for the typical question, which one should I use or which one is the best, is as always, it depends. So, in general, always try to evaluate requirements of your application carefully and be sure you fully understand the consequences of choosing a particular framework. And also, try to fully understand its internals, as improper use may have like disastrous consequences. For a programming model, I think most of you guys would prefer high-level API, and it makes sense, you know, it's more elegant, more productive, and so on. But on the other hand, high-level APIs might hide a lot of details. You will have to understand once you're facing an issue. And I have seen a lot of problems with that. So I would recommend following. If you want to do like a lot of data science, analysis, or if you want to play with REPL, I think the high-level API is a great way to go. But if you expect more data-intensive operations like crunching terabytes of logs, or if you want to manage your DAG really precisely, compositional API might definitely make sense. So think it through, what do you need and which approach suits you better. I would also recommend go for a framework with all diverse semantics available, as you usually don't want to limit yourself, especially if you're not sure what to expect. And as you all know, this is quite common in our industry. But of course, there are definite use cases when at least once or at most once delivery guarantees are all we need. Also keep in mind, which might be a little bit surprising, a system supporting exactly one guarantee doesn't have to support weaker guarantees. And yes, I'm talking about Spark streaming. This point might be tied together with the previous one a little bit, Most of the streaming applications are stateful, and as we have seen, this area might be challenging. So the state management of a particular framework should be really up on your evaluation list. Lastly, make sure your system is able to recover quickly. You can use Chaos Monkey or similar tool for testing, because as we discussed, fast recovery is crucial in stream processing. Remember, data are still incoming. And now let's take a look at particular frameworks. Storm is still a decent fit for small and fast tasks. If you care mainly about latency, Storm might be a good way to go. But also keep in mind the fault tolerance or Trident state management hurts performance a lot. An interesting option might be a potential update to Twitter's Euron, which is designed as Storm's replacement and should be better in every single point, but it also keeps the API. And the best thing is, Euron was open source very recently, literally just a couple of weeks ago. It is a little bit uncharted territory, but if you like Storm's API, it's definitely worth to check this one out. For Spark streaming, you should definitely at least try it if Spark is already part of your infrastructure, because in this case, streaming comes basically for free, and you can also take an advantage of various Spark libraries. Apart from that, there's a bunch of helpful tools available like REPL or Spark Notebook for the data exploration, for example. Spark's ecosystem is really impressive. But you should always keep in mind micro-batching limitations, which may really become a showstopper. Also, be sure latency is not critical for you. When thinking about adopting Samza, Kafka should be a cornerstone of the architecture. I know it's pluggable, but nearly everyone, or maybe everyone, is using Kafka, so I'd stick with that. Also, as mentioned before, Samza is shipped with powerful local storage, and it's great for managing large states. It can handle states of tens of gigabytes easily, which is pretty nice. But keep in mind Samza's at least once daily limitation. Also, if you like Samza, you should also consider newly introduced Kafka streams, which offer similar functionality with a little bit nicer API and are operated by Kafka itself. Basically, a Kafka stream is like library of Kafka. So this is a really big win for operation, as Kafka is basically all you need. If you prefer low-level / compositional approach, and you are also Hadoop positive, I believe Apex might be a great choice for you. It gives you fine-grained access to DAG, so you can get really most of it. Therefore, its performance, especially achievable latencies, are truly excellent. Moreover, Apex allows dynamic DAG changes, which is kind of unique feature. As you see, Apex offers interesting options, which, as I believe, overweight its emerging but already graduated status. Flink is conceptually a great streaming system which fits very most streaming use cases, and it often provides progressive functionality like advanced windowing or time handling, which may not be implemented by its competitors. So you should always consider Flink when you need a functionality, which might be hard to implement in Spark or generally in any micro-batching system. And apart from that, Flink also has an API for the batch processing, which may be pretty useful. But you need to have enough courage to adopt an emerging project, and also do not forget to check out its roadmap. And the last thing I want to mention today is Dataflow and its open source initiative. Dataflow is a part of Google Cloud Platform, and Cloud Platform has all sorts of things in it, as huge data storage, BigQuery, Cloud PubSub, some tools for data analysis, and so on. And also aforementioned Cloud Dataflow. It is Google's managed service for batch and stream processing with unified API. And it's built upon well-known Google technologies such as MapReduce for batch processing, Flink Java for programming model definition, and Millwheel for stream processing. And all of them are really good. It's Google. You may be asking why I'm talking about that. As I said, I will be speaking about open source frameworks, and this is clearly Google's proprietary solution. But Google decided to open source Dataflow SDK recently, and guys behind both Spark and Flink have implemented its runners. So now we have an ability to run jobs defined by Dataflow API in Google Cloud Platform, in Flink or in Spark. And it's very probable more engines will follow very soon. Dataflow provides API in Java and in Python, implemented by Google itself. And also I have found a couple of Scala DSLs already. Apart from that, Google and a number of partners submitted this as a new Apache proposal named Apache Beam. I think Beam has a good chance to be the unifying API that gives us a nice way to write once and run everywhere. But it's important to say all of this is quite recent, and the implementation of the promised features might be missing. But definitely worth to check this out. So now it's time for questions. So do we have any? But also I'll be around anyway, and always happy to discuss various stuff. So just find me. I'm usually around our booth. Okay. Thank you very much. Okay.